Yeah, actually I wanted to show Greg's thing again. I mean, it seemed to be working on my computers finally, and then somehow here it doesn't work again.
Well, it's because you have to compile everything. That's the problem with Mathematica.
Yeah, I mean, I know. I press Shift Enter. I activate the kernel, right? But then it got stuck. I don't know why.
Okay.
You know what? I just realized today that we were actually taping the whole thing.
Oh yeah.
What's up, you? I didn't know that.
You're gonna go to YouTube, right? After that.
YouTube?
You have to sit there and edit you out.
So just to be safe, so here's what we did last time. I hope it was not very fast, but the main thing that we observed is we spoke about three-dimensional inversion. So if you have this time a sphere S, and inside of the sphere you have another sphere K. Well, to understand what inversion is doing in this case, you just take it again. If this is sphere of radius capital R, then let's say here's a point. It's gonna just map this point so that the product of the distances of those points are again R squared, just like before, right? So in other words, three-dimensional inversion, if you are just doing that for a point, can always be understood as just inversion in a circle, right? So because of that, what you can do is you can just find the plane that bisects both the sphere S and the sphere K. And then you see that we have now this circle here, and then we will have some other circle here, because we know that two-dimensional inversion is mapping circles to circles, right? And then all you have to do is you just take this blue line. You take this blue line that goes through the centers of both S and K. And what do you do with this line? Generate the full picture. All you do is just rotate around this blue line, right? So by rotating, I'm saying that when you rotate, you're selecting another circle on S, another great circle on S, and that will create another exactly of the same shape circle as that great circle of K. And that tells you that spheres are going to be mapped to spheres. Make sense? All right. And what do you know? If spheres are mapped to spheres, that right away tells you that circles are mapped to circles. That's because if I have two spheres, I just don't want to draw it actually, right? If I have two spheres, they intersect in a circle. Those two spheres will be mapped to spheres. The circle of intersection will be mapped to another circle of intersection. Okay? Now, if the sphere K happens to go through the point Q, through the point of the center S, then what will happen to the sphere? What will be the shape of it through inversion?
Can you say it again?
Yes, if the sphere this time was something like this, what would happen to that sphere? What would it look like? If I select a sphere, what would happen to that sphere?
I'm not sure I'm following the pictures. The whole thing is a sphere, S2, and then you have another sphere embedded inside.
Yes, precisely. You have one sphere sitting inside of another sphere.
So that's not on the surface; it's inside.
Well, here is the big sphere S,
Uh-huh.
and here is the inner sphere. This red.
And then the sphere just touches the origin?
Yeah, and this sphere is touching the origin. What would happen?
That would map also the same way.
No, not.
We'll map this a lot bigger further out. Sphere, no?
So I was going very fast. All right. What would happen if it were a circle? If it were a circle through the origin, what would be the image of a circle through the origin of S?
If you rotate it, you create a sphere.
Well, yes, if you rotate it, this would be a sphere here, but what would be the image of that sphere?
The circle goes through that big circle now. Like it's so.
So here is Remember this thing we did. So what you do is, you find this point, the image of this point. It's going to be, say, somewhere here. If it is a circle, right? It'll be somewhere here, and observe that if this is the diameter here, the angle here is 90 degrees. And the angle of a line is 90 degrees. What will happen to this point? Again, it's carried here. So as I'm rotating around the circle, as I'm rotating around it, that will be moving this point farther, and then I'm going to be moving in that direction.
It's going to map to line.
It's going to be mapping to a line. Make sense? So we did it before, and if you look, we have a lot of pictures in visual complex analysis. You have a lot of pictures of that. So that line will actually be parallel to the tangent here. Make sense? It will be parallel to the tangent here. You see that? So how do I now generate a picture for the sphere? Now imagine that this is just a cross section of a sphere. Now what would be the reflection of this small sphere?
Would be a plane.
Would be a plane, exactly, because all you have to do is just take this dotted line and rotate it. By rotating this dotted line, I have selected another great circle, and therefore inversion is now happening. I just am reducing inversion in 3 dimensions to lots and lots of inversions. I'm reducing the inversion in 3 dimensions to lots and lots of inversions in 2 dimensions. Make sense? Right? So this is somewhat useful, especially when you go on. I actually brought force. Yeah, I mean, that's one thing. But for example, if you look into elliptic functions, I'm not sure we'll cover that, but if you look into, let's say, pictures like this, do you see that? Right? So force nonchalantly will just kind of go very fast through that, and then say, well, it's clear that this is mapped there and that is mapped somewhere else, right? So I'm hoping that this type of thing will help you. Right, very heavily emphasized is Mobius transformations, especially once we get to chapter 8 in Stein. That will be emphasized there. And it's emphasized on the qualifying exam especially relative to automorphisms of the disk, stuff like that. Okay? So I'm just hoping to give you a good picture of Mobius transformations as soon as possible. So you see that if I select another great circle, I have another line. And therefore, when you glue those lines together, you're seeing a plane. And since inversion is involuntary, in other words, it's its own inverse, then you know that any plane will be mapped to a sphere through the origin. Okay? So that's the thing we learned. And similarly, we just kind of can take the 2-dimensional picture that demonstrated that this circle K was mapped to another circle. And then by applying it many times, by rotating, you see that any sphere that does not intersect the center of the sphere of inversion will be mapped to another sphere. Okay? So in other words, we see that this interaction, spheres can only be mapped into planes or other spheres. And that's really annoying to say planes or other spheres. They are all the same. Now you can make them all the same. How? You can make them all the same is when you consider stereographic projection.
You have to remove a point.
So stereographic projection is giving you a new picture of the complex plane. It's actually giving you a compact version of the plane, which, by the way, really confused me when I was doing some exercise. Some of the exercises I assigned, I'm going to show you, right? So then it will be relevant. But I made a big mistake because I know what continuous functions are supposed to be doing, and something that was happening in complex analysis seemed to me to be contradictory to what continuous functions are supposed to be doing. But it's not, right? So here's what stereographic projection is doing. So what you have is you have a sphere, and this is the Riemann sphere. in visual complex is denoted by sigma, and it's of radius 1. And the sphere is inserted in the complex plane. Okay, the sphere is inserted in the complex plane, and the way you translate points of the complex plane onto the sphere is this is your north pole, and select any point z, and just check where z intersects the sphere, where the line through z and n intersects the sphere, and that's going to be the corresponding point on the sphere. And you can go back and forth. The advantage is that now the point n, what does it become? You can see that as I push z farther and farther, in any direction I choose, the line is, this point here is going to go closer and closer to n. Right? So I can think of the extended complex plane. In Conway's book, it's denoted by C infinity. That's the extended plane.
I'm sorry, please repeat this. What do you mean by?
Say it again. What I mean by what?
You said a point getting closer to.
Yeah, so take the z, move it farther.
Okay.
Anywhere, in any direction you like. What do you see happens to this point? This point is going to get closer and closer to the North Pole. You agree? Visually, right? Just you can actually prove that, but we had formulas for them. If you want to, you can use the formulas, but you can do that visually. Move z farther and farther in any direction of your choosing, and this point is going to be closer and closer to n. Right? So the picture for the complex plane is actually much better when you have the extended complex plane. Instead of thinking of the complex analysis as done in the plane, you can think of complex analysis as done on the sphere. Okay? So for example, if I multiply, if my function consists in multiplying by e to the I theta, that corresponds to taking the sphere and rotating it by the angle theta. If I take 1 over z, if I apply z is mapped to 1 over z, we showed before, what does it do to the sphere? It's going to rotate it by 180 degrees around the x-axis. Okay? So I can think of a lot of motions that's happening on the sphere. And the sphere is compact. The plane is not compact, but the sphere is compact. Okay? So if I think of it, if I think of the extended complex plane, I can think of it as being compact. Right? And that's something that that was, I mean, when I was studying, this was confusing me, because in neural analysis I'm trained to think, okay, well, here is an unbounded region. How can an unbounded region be mapped by a continuous function to a bounded region? Basically, back and forth, in other words. So how can there be an isomorphism between an unbounded region and a bounded one? Because bounded one will be, you can contain it, it will be compact. It will be contained inside, it will have to be bounded.
Yeah, but you still need to remove a point.
No, you don't need to remove anything. And now n can be thought of as the same point as before. So here is the picture that we have for the complex plane. I can think of this as here is 0, and if I move in any direction whatsoever, what's the point here? This is the point at infinity. This is the point at infinity. This is the point. This is infinity. This is infinity. All the same point.
So you're just making an identification?
Yeah, I mean, in other words, the entire plane, you see, it just unfolded. All those things, if you just glue them together at n, that would be the same point. I identify every direction. So the neighborhood of infinity will be just select anything avoiding, let's say, some bounded region. Select any disk around the bounded region. The complement is, in some sense, can be thought of as bounded on the Riemann sphere. You understand? This is the bounded. Inside of the disk is bounded. Outside of the disk is unbounded. Right? This is bounded. This is unbounded. But on the complex, on the Riemann sphere, it's all the same. There is no such thing as unbounded. This is bounded, and this will also be bounded. Right? This will just be some neighborhood here, some sort of hat around n.
But then, you know, if by saying that, we're saying that the sphere is homeomorphic to that if you take a quotient space, because you're identifying.
Yeah, you can think of it. You can think of it if you prefer. But again, I mean, really, infinity was not even part of the complex plane to begin with. We had the extended complex plane, and then I just create machinery that represents what are the operations that are happening there, right? So I can think of the extended complex plane as just the Riemann sphere. And one important thing to notice about the Riemann sphere is that it is in fact, I mean, what happens to circles? What's happening if I select a circle here around Z? What would be the image of that circle? It would be some shape here. What would that shape be? You see? Well, again, right? So again, really sorry that I went fast. It will have to be a circle. Has to be circle. How do I know it has to be a circle? A very good explanation is that actually the operation of, look at it. What we do is we take, how do we create this point? We take a line and we map it onto the, we take a line connecting the North Pole to Z. Right? That's very similar to what you do when you consider inversion. In fact, the stereographic projection is, everything about it can be understood by understanding inversion. It is inversion. Okay? Now here is how I know that what's the inversion. So it's kind of difficult to draw it in 3 dimensions. I'm going to look at it on the side. I'm going to place the picture on the side. So here is that picture on the side, and here is the Riemann sphere. So this is -1 and this is 1 if I just chose to isolate the x-axis here. And this is the North Pole. Now, what I can do is I can select a circle. For now, just think of it as a circle. Select a circle whose center is n. Whose center is n, and it extends here. Okay, we have this. This is our circle. Now, what can you say about the radius of that circle? The radius of that circle is √2. Do you agree? Because this is 1 and 1. The radius is √2. Now let's see. Let's now forget about stereographic projection for the moment, and just think about inversion in this red circle. So what is inversion in the red circle going to do to the points 1 and -1? Map to themselves, because what you do is they are located on that circle. The distance is already √2, right? So the product of the distances must be 2. So of course that's the only choice. The only choice point that will satisfy is here and here, right? So you can see that those points are preserved. Now, what must it do to the Riemann sphere? What's going to be the image through if I just take the Riemann sphere and I invert it in this red circle of the Riemann circle? Let's call it circle for a moment, right? This is part of this Riemann sphere. It's a great circle in the Riemann sphere. So what's going to be through inversion the image of that cross section of the Riemann sphere?
Oh, it's like
You see, it goes. This Riemann sphere, the circle goes through the center of the red circle, right? So we know that that it must be a line. Just by the pictures we did before, it must be a line. Agreed? Now, what sort of line must it be? Well, first of all, I know it must be a line. But the simplest thing I can say, you don't need to even overcomplicate it, right? It must be a line. Okay, but this line must contain which points? It must contain the points 1 and -1. Right? It must contain. Now you know that through any 2 points there's only one line. That's it, right? So it must be the x-axis. The image must be the x-axis. Do you see that? Now, do you see that? So the image is the x-axis. Now, if I select any other cross section, if I select, let's say, the cross section coming here, it's going to be another line, and that will be the y-axis. Now the fixed points are I and -I. Do you see that? If you come through here, you would have another great circle. And this great circle is perpendicular to you. Yep. And then what you have is fixed I and minus I, and again we must have a line. Now rotating that picture gives you a three-dimensional inversion, and therefore the three-dimensional inversion of the Riemann sphere is the complex plane. And of course you have the point of infinity, right? It's going to be the complex plane. Make sense? And now you understand. And now you can see by drawing those lines, you see that that's exactly what you do when you what's going to be the image of any point. The way I select and I find what's the image of this point on this Riemann sphere. Here is a fixed point here. Here's some point, and then I just do this. I just draw a straight line through that point. That's what I do when I do stereographic projection, right? And I see where it meets the complex plane. But we just said that drawing this line. Here is a point on the Riemann sphere, and here is a point on the complex plane. There must be symmetric with respect to each other because the Riemann sphere is mapped to the complex plane by inversion. Okay, so because you know what inversions are doing, you right away know that stereographic projection will always map circles to circles. Okay, now any straight line can now be thought of as a circle. You see that as well. Any straight line. If you have a straight line in the complex plane, that's just going to be a great circle. Any straight line in the complex plane is going to be a circle that goes through the North Pole. Yes?
Are the radii of those two circles different, or
yes, they are different. They are usually going to be different, of course.
Okay.
Right? And this point Z, this is not going to be usually the center. Okay? It's not going to be the center. Okay? So all we know is that circles are mapped to circles. We don't know that centers, which is by the way not true in general. Centers of circles are not generally mapped to centers of circles.
Then can I say one is always bigger than the other one?
Depends actually, right? They could be.
I mean, think about it. One is on a plane and the other one is on a curved surface, so it's not going to be...
If it's, for example, if you take the image of this circle through the plane, this one, right? It's going to be mapped to itself, for example, right? So they can be of the same size, or one is bigger than the other, yes, right? They're either of the same size or one is bigger than the other. There are no other possibilities. Okay, right. But this is really, again, right? A lot of those things are complicated. So I'm hoping you're picturing. So now what we do today, we talk about. So remember the properties of Mobius transformations that we mentioned. So we know that Mobius transformations will always map circles to other circles. You can now say, right? So in other words, that includes now lines. Circles that are. Infinite circles. If I have a circle that has the point infinity, then if I project it onto the Riemann sphere, that's going to be a great circle. Sorry, that's wrong. It's not going to be necessarily a great circle. It's going to be it's just going to be because you can have a picture like this. You can have. I'm sorry, I called it a great circle. Great circle is a circle of radius 1. But if you have the point at infinity, you can have circles like this, right? Oh, sorry. You can have circles like this. Yeah, all of those things are not great circles, but they're going to be mapped to lines. So sorry for confusing you there. But they're going to be mapped to basically lines are going to be mapped to circles on the Riemann sphere that are going through the point at infinity, through the North Pole, right? And then you can see that again by thinking of it of stereographic projection as actually it's just inversion. Okay, make sense?
Hawaiian ring.
All right.
Hawaiian ring. Have you seen it?
Yeah, I guess.
Like a union of S1s identified at a single point. So just
again, right, remember that what we did is we said that m of z is equal to az plus b over cz plus d, which if you break it apart, it's a over c minus 1 over c ad minus bc over cz plus d. So by looking at this expression, you see that this is just a translation. This is some dilation with rotation possibly. This is again something of that sort. But the denominator is really 1 over z. Right? By understanding 1 over z, I understand what the Mobius transformation can do to a circle. So what can happen is a circle will be mapped to a circle. Because if you just take conjugation, right? Then you know it's going to be the formula for inversion with some modification, and some dilation, and some translation, and some rotation, right? And we know then that it's going to be mapping circles to circles. All you have to do is just now reflect, okay? And we know that it's conformal because it's differentiable. One easy way to know it's conformal is that this function can be differentiated. Okay? If you want to know what's going to be the value of the derivative at infinity, just replace z by 1 over z. Why? Because the function 1 over z is going to rotate the Riemann sphere. Place it, basically it will be 1 over z. At 0 is the same as infinity. Okay, we're going to learn that more actually when we get to chapter 2 in Stein.
Professor?
Yep.
If we know that all holomorphic functions are conformal, then why do we need another definition? Like why do we call it conformal maps instead?
Well, conformal, to be precise, a holomorphic map is conformal as long as the derivative is not 0.
Okay.
If your derivative is 0, then you don't say it's conformal, right?
Okay.
But why? Is because if the derivative is 0, it's crushing everything to a point, right? The sense of an angle does not have to be preserved there, because everything is crushed to a point. If the derivative is not 0, remember we just had this analogy, the differential map, the derivative of that function, it's going to be like a linear map that is preserving the angles of the edges of the shape that you are taking, if the shape is smaller. Okay? So that's how you know differentiable non-zero derivative functions are going to be conformal. So that means angle preserving. And that's because m prime of 0 does not equal to 0 anywhere. And of course they map circles to circles. So I hope you understand that the straight line is also a circle. Right? Just take any straight line, project it, and that would be, because of inversion, that would be a circle that goes through n, with the sphere. Yeah. So circles are mapped to circles, and we mentioned last time that coefficients are not unique. A, B, C, D, not unique. So a Mobius transformation can have lots and lots of A, B, C, D. And that's because what you can do is just, instead of this formula, you can just multiply by k. We have akz plus bk over ckz plus dk is again the same thing as mz for any k not 0. Okay? And take care. Yeah, sorry. So, what else do we have? So we have this, and one thing that we can impose, we can actually pick k if we pick k to equal to either plus or minus 1 over the determinant AD minus BC, then the new coefficients so A prime equal to AK, B prime equal to BK, you get the point. This map is then going to be called normalized. MZ equal to A prime Z plus B prime over C prime Z plus D prime. With those coefficients, this is normalized. Normalized. In other words, determinant is going to be 1. So you have that A prime times D prime minus B prime times C prime is going to be equal to 1. You can make it equal to 1. Now, this has several advantages, though. One of the advantages is that if I look at the coefficients A prime, B prime, C prime, D prime, I can find the inverse, and the inverse will be 1 over the determinant, which is 1, and what we do is we have D prime here, A prime here, minus C prime minus B prime, and those are the coefficients. We have the formula the inverse of Z, M inverse Z, is going to be D prime Z minus B prime divided by minus C prime Z plus A prime. That's going to be the inverse. That's going to be the inverse Mobius transformation. Yes?
So if we don't have unique parameters,
Yes.
do we have any implication? Because looking at the determinant, if I choose parameters a certain way where I have determinant 0, or is right?
You will never have determinant 0. If determinant is 0, look at this expression, then the Mobius transformation is constant. So it's not going to be an interesting case. So determinant can never be equal to 0. Otherwise, it's just a constant map. Nothing interesting about it.
Okay.
Okay?
But otherwise, having not unique parameter addition doesn't cause any problem, right?
No, I mean, in fact, what I said, you don't need to convert it to the normalized form to find the inverse. You can just do that for any A, B, C, D, and that would be.
But before even normalization, right?
Mm-hmm.
You said that A and B and C are not unique, right?
Yes, they're not unique, and very simply, you just multiply by any constant, and you have them. I mean, really, you study differential geometry, what's happening is it's a projective space. So Mobius transformations are produced from linear maps on C2 cross C2. So those are homogeneous coordinates. And what you do is you collapse the space by one-dimensional complex spaces, and then you get Mobius transformations. But then I don't want to necessarily go into those details. You can actually read it in that book.
Which book?
Actually, even in visual complex analysis, it's talking about homogeneous coordinates. Okay, so this is the inverse, and one reason we're not actually necessarily going to go into the details. One reason that you might prefer normalized coefficients is that with normalized coefficients you have an easy study of the fixed points. You have a good equation for the fixed points. So in other words, you're interested to know which points is the Mobius transformation not going to move anywhere. That's actually going to be pretty important. And then you can classify what is the Mobius transformation doing to the space. What sort of transformation is it? Okay. So that's really for perhaps dynamical systems and other stuff like that. So in general, if you just take the inverse of the matrix and forget about disregard the determinant, you will always get the coefficients of the inverse Mobius transformation. Okay. So Other properties that I wanted to mention is that, again, we spoke of them several times, but let's say again, if Z and Z star are symmetric.
Z star
is just another point. It are symmetric with respect to circle K1 and K2 is equal to the image under the Mobius transformation of K1. Then M of Z and M of Z star are symmetric. With respect to K2. So that's called symmetry principle, very important. So what does it mean? What's the symmetry principle? Is that so Z and Z prime are symmetric, which means that I hope you remember this. If this is Z and this is Z star and this is K1, okay? Symmetric means what? Means that there exist. So that first of all, it means that the what do you call it? The inversion of Z through the circle K1 will be Z star. Okay, that's what it means. And they are going to be, and if it's so, they must lie on an intersection of any two circles that intersect K1 and go through Z and are perpendicular to K1. That's geometrically what's happening. So now, if I apply any Mobius transformation M, K1 is going to be mapped to another circle K2. Right? And those two circles that I drew here are also going to be mapped to other circles. But those, because the map is conformal, those circles will have to now still be at right angles with respect to K1. So we have another two circles, again they're at right angles to K1. And this is M of Z, let's say. It could be that M of Z is here, I don't know. I don't know what the Mobius transformation is doing, but possibly it's mapping the inside to the inside. We're actually going to talk about it in a moment. And this is MZ star. So again, they are, you see, because they lie on the intersection of two orthogonal circles, they must be inverses with respect to K2. Yes?
Because, so did you apply first Mobius transformation to K1 as well to get the Z star?
To K1, well, I mean, I apply the Mobius transformation to K1, and that will map this circle K1 to another circle K2.
But if I understand that, but if when you said, for example, we are basically applying the inversion through to Z through K1, right, circle. Now we get the Z star.
Well, I mean, I don't even, what I do is I just apply M, right? And then I check for symmetry. I apply M to the entire picture. So Z will be mapped to MZ, I don't know where MZ is to begin with, a priori I don't know where it is, and then we have some M of Z star. But what do I know? Those 2 points will be mapped to the intersection of those two circles, right? So Z and Z star will be, again, will be still, M of Z and M of Z star will be the intersection of those two small circles.
But if I just take K1, for regard, right, and I just apply the Mobius transformation over there, I'll get the picture on the K, what I'm looking on the left side right now.
Yeah, it could be, and this, by the way, could be a straight line. I mean, I just decided it's a circle, right? So each of those circles might potentially be mapped to a straight line. But the point is that the angles will be preserved. So those two circles will be, they're intersecting, and the map M is 1-to-1. So it will take this the picture of those two intersecting circles and will map it to another picture of two intersecting circles. And those two circles, they had 90-degree angle with respect to K1, so they now have to have a 90-degree angle with respect to K2. Okay? So in Conway, I actually posted Conway on this website. If you want to, you can look there. he does it analytically. It talks about all those operations in terms of the cross ratio, which I'm going to introduce. But I think it's easy to see by this picture what's happening. That's called symmetry principle. Okay, so that Mobius transformations preserve symmetric points. All right. And again, this normalization is important when you study fixed points. So I actually let's place it at 6 fixed points. So fixed points is I want to know when mz is equal to z.
You mean number 5?
I guess so. So fixed points, I want to solve the equation mz equal to z, and that is going to be az plus b over cz plus d equal to z, which implies that az plus b, well, I mean, let me just already cover it. So just if you group everything together, you just have the equation cz squared plus d minus a z minus b equal to 0. So that means that at most 2 fixed points. Right? If more than 2, then mz is identically going to be equal to 0. Understand? If I have 3 or more different points that are fixed by the Mobius transformation, it must be the identity map. Here we say it like this. Okay, it must be identically defined to be Z, and that's very important property. So again, now new stuff. So I'm hoping it makes sense. So cross ratio is going to be our way to try to create specific examples of Mobius transformation. So I want to know how specifically I can carry one circle to another circle. Can I do that for any 2 circles? Or maybe there are some circles that I can never get to from other circles. Okay? So what you do is, first of all, if you select some circle, select any circle K1, and select a collection of points. So select the point Z2 anywhere in the circle. Select any other point Z3 and Z4. So I'm not going to define it, but do you see that on a circle, in order to orient myself, I need to mention 3 points. Right? If I mention just 2 points, I can go from this point like this, or from this point like that. So I need to mention 3 points to indicate how I'm walking. Okay? So first I'm at Z2, then I'm at Z3, then I'm Z4. So that's called orientation. So let's maybe just.
You can give an orientation to a circle even with just 1 point.
No, I mean with 1 point. With 1 point, you're just standing there, right? Orientation is telling you how you're walking.
You say counterclockwise or clockwise or whatever.
Well, yes, if you want to go counterclockwise again, but then you can indicate it by 3 points. So we're going to say that Z2, Z3, and Z4 is orientation. Or 4K1. So in other words, I specify how I'm moving using those points. So first I'll be at Z2, then at Z3, then at Z4, and then from Z4 back to Z2. So that gives me, you can say counterclockwise. I just gave it a counterclockwise description, right? And then imagine that what I want to find is I want to create a map that will carry this, and just first for over just a straight line. So I'm just going to take this and make it into a straight line, and I'm going to take Z2, and I want to take Z2 and place it at 0, and I'm going to take Z3 and place it at 1, and Z4, I'll place it at infinity. So I chose 0, 1, and infinity, so I give this positive direction here. Okay? By the way, what would be if I move here? What would be the point here? So this is 0, 1, this is minus 1. What's the point here?
Z4.
No, I mean, well, Z4 is not visible. Z4 is what's mapped. So this is infinity. What's the point here?
To Z.
You go back to C4. It's not-
Well, in terms of this, well, in R you know that this will be minus infinity, but here there is no such thing. It's the same exact thing.
Yeah, that's
So there is no minus infinity. There is only one infinity. Okay.
Okay.
So this is infinity, and this is again infinity. It's now a closed loop because this is the North Pole, and this here is also the North Pole.
kind of like an exact sequence. Instead of zeros, you get infinity.
Yeah. So we have that, and in this case, you see, I drew you a circle, but you see, you could have selected arbitrarily any point Z2, any point Z3, and any point Z4. You agree that once you select 3 points, you have a circle, a unique circle will go through those 3 points. If they happen to be collinear, that unique circle is a line, right? But if you need to select 3 points, and that is enough to determine the circle. You agree? So we selected those 3 points, and we have this. So the formula that I'm giving is, let's try this formula. C of Z will be, it's called the cross ratio, and it's denoted usually as Z, Z2, Z3, Z4. And in this case, they're all finite points. So I can have, first is that it's the formula that I've written already last lesson. And that is, you see, Z2 is mapped to 0, and Z3 is mapped to 1, and Z4 is mapped to infinity. So what I do is, I would say that C of Z is Z minus Z2 over Z minus Z4 times Z3 minus Z4 over Z3 minus Z2. And that is if Z2, Z3, Z4 are all in C. None of them are infinity. Then this formula makes sense. I can create the other formulas are, I can say C of Z is going to be equal to, say, Z3 minus Z4 over Z minus Z4, and that's if Z4 is a point at infinity. If I chose Z4 to be infinity, then you can check that this will work, right? Infinity must be Z2, sorry, what am I saying? Z2. Sorry, Z2. So if I plug in infinity here, that will crash it to 0. So that's working, right? So that's Z2 is that. And third formula is C of Z is Z minus Z2 over Z minus Z4. And that's if Z3 is infinity. And the last formula, formula 4, is C of Z equal to Z minus Z2 over Z3 minus Z2, and that's if Z4 is infinity. Okay? I mean, you can verify all those formulas. Just check them and think about them, and I don't want to spend too much time here. Just think about it and you will be fine. So first I want to ask you is this. So in this picture we have Z2, Z3, Z4. What is it going to do to the circle? I only know that Z2 is mapped to 0, Z3 is to 1, and Z4 to infinity. That's what this formula is doing, right? But what is it going to do to the circle and why? Anyone? What is it going to do to other points? If I select a point W, for example, I select here is Z2, and I select a point W. Please tell me, where will I find this point W and why?
Won't be in between Z2 and Z3?
It will be still between Z2 and Z3, it will be somewhere here, right? That's where W is here. But how do you know? Well, a Mobius transformation, what is it doing? It's mapping circles to circles. You agree? It cannot violate that property. So if it mapped Z2, Z3, and Z4 onto this line, it must map the entire thing onto that line, because every other point in EW must be still on the same circle. So the only way EW will be on the circle is if it's on the line now. Make sense? So it has to be real.
It's like open circle sitting on.
Yeah, the circle is just, you see the infinity. Just the way you see it's a circle is you look at the Riemann sphere. The Riemann sphere is just going to be again, and how I know again, I'm hoping it makes sense. I'm hoping that you all see that is that if I take the stereographic projection of a line, that must be because it's going to be the same as taking inversion, right? It must be a circle, and that circle must be going through the center of inversion, which is the north pole of the Riemann sphere.
And those are your infinity points.
And those are my infinity points, exactly, right? So it has to be a circle. So note, C of Z is the unique Mobius transformation that does this. Mobius transformation on Mobius map that carries Z2 to 0, Z3 to 1, and Z4 to infinity. Because if S is another map, if S is any other such map, all I have to do is just do this. So I can take S, compose it with the inverse, right? Taking an inverse of a Mobius transformation, you can just verify by just simple calculation, and we already talked about it. It will be another Mobius transformation. So C of S inverse is a Mobius transformation, and what does it do to the point? What does it do to the point 0? What's the image of 0? 0. Exactly, right? Because look at it. What is C inverse doing? If S is carrying Z2 to 0, S inverse will carry 0 to Z2, right? And then C of Z2 will be back 0, right? So this is 0. C of S inverse of what other point am I picking here? 1. That will be 1. So we already have 2 fixed points. And then last is C of S inverse of infinity is infinity. Okay, so that implies, because we have three fixed points. 3 fixed points implies that C S inverse of Z is simply Z everywhere, which implies that C of Z is equal to S of Z. Okay, so that tells us that it's unique. And that's again from investigating the fixed points.
If we are taking our Mobius transformation to carry those points, like C2 to 0, C3 to 1, C4 to infinity, why do we have those cases where we have to consider?
The formulas are this formula is using finite numbers, right? Otherwise, just with infinity, it's still, if you think of it as a number in the complex plane, it's not so simple to deal with it in a formula like this. But you just check that those formulas they work. They work for Z. You can just come up with them on your own. There's no need to check anything. Right? Just come up with this formula on your own. That's what you should do. Okay? Yeah, just come up with this formula on your own. Come up with this, with that, with that. One warning is that you see now my discussion follows a little bit more Conway's discussion, and Conway defines the cross product in the opposite way. I'm not sure why he prefers that, but Conway defines defines the cross ratio as going in this direction. Understand? Gives it a different orientation. I guess he likes the unbounded region to be mapped to the unbounded region, but we'll talk about it. In this case, this bounded region will be mapped to the upper half plane. Right? And maybe for some reason Conway prefers something else. Okay, but it doesn't matter. It's really all pretty much the same.
Listen, I'm trying to visualize basically when you're mapping Z4 to infinity.
Yeah.
So the circle that basically passing through the Riemann sphere, right?
Yes?
What does it mean by Z4 being at infinity? I mean, what?
It's mapped to infinity. So
I'm just trying to
It's
draw
like-
a picture, kind
It's
of
like acting as the North Pole in that case.
but how big? I mean, is it like, is it going like an infinite, like a circle over there, or what?
I'm not sure I understand your question.
When I, okay, so we have a point, so we have a circle right now,
Uh-huh.
right? And we have one of the point on the circle is Z4.
Yes.
And the Mobius transformation is mapping that to Z4 to infinity.
Yeah.
So what I'm trying to do is just simply trying to make a picture out of this, that, okay, this circle is kind of in the Riemann sphere.
Well, I mean, you see, if you prefer, I'm not sure it's so easy to, because you have to picture the circles as lying on a three-dimensional object, but really you can think of this, you translate this via stereographic projection, translate this circle to the Riemann sphere. Now it's basically we have a sphere and on it we have one circle. Now this line is going to be another circle. So what we're saying is that we take the circle and somehow carry on another circle, maybe expanding it, doing stuff to it, rotating it, but carry one circle to another. Right? It's not clear by this procedure how I am exactly, what exactly I'm doing geometrically to this thing. Not quite as obvious. I'm going to make some other remarks about what happens to the insides, but it's not pictorially. I don't think it's so very obvious. All I know is just you can think of this as one circle, and the image is some other circle that happens to touch the North Pole. Okay, and then if I just do that on the Riemann sphere, I see just two circles moving. But if I project it back on the complex plane, that looks like a straight line.
So this line, as a matter of fact, is another circle.
Yes, that's exactly how you should think of it. It's another circle. All right. So. All right. So. Right away from here, we see we know that we already have a unique map that will carry the circle to a horizontal real line. So maybe I should make another note. Note Z is a point on K1, on the circle K1, if and only if the cross ratio Z, Z2, Z3, Z4, complete my not necessarily equal, but complete my sentence. See if you can figure it out. So Z, I drew here a W, but so some Z is on the circle K1, if and only if the cross ratio of that Z with Z2, Z3, Z4 is what?
So we map somewhere.
Yes, and then what does it mean? That it's real. You see that there's a circle, and now this is the x-axis. So if and only if this is real. Make sense? Because again, you see circles are mapped to circles, right? And this circle is mapped, is basically mapped onto R. So that's what it means. Yeah?
Can you elaborate a little bit? You said on the left side, we don't look at it as the minus infinity, but here we are saying that this map is kind of real axis.
Well, I mean, it maps to the real axis, yes. In other words, this is the x-axis.
Right, but then,
The positive axis, right?
right.
Yeah.
But then on the left side, you have the infinity, not the minus infinity.
Yes, this is the difference. In complex analysis, right, it's a little bit weird at first, maybe. But you don't have minus infinity. You just have only one infinity. Because all of them are the same. This point and that are identified. They are the same. Right? In real analysis, you just think of it as an unbounded line. But here, you think of this really on the Riemann sphere. You just right away translate this picture. What is that? It's on the Riemann sphere. If I go all the way there, somehow I reach the North Pole. And then I continue walking from the North Pole, I'll start walking from here, from the negative numbers. Okay, so you are walking in a circle.
Got it. Oh, I see.
Yeah.
Got it.
It's a little weird, but I understand that there's no minus infinity.
Yeah,
There's only infinity in
Yes.
both directions. Yeah.
Okay, I think
So,
that,
all right. So this is only R. And now proposition. You see, why do we like the cross ratio so much? Is because of the following propositions. Is that first of all, if Z2, Z3, Z4 are distinct points, and T is any Mobius transformation, then, and I'll try to explain by picture, then it's invariant, so the cross ratio is invariant under this transformation. Then Z, Z2, Z3, Z4 ends up being the same as T of Z, T of Z2, T of Z3, T of Z4. So cross ratio is invariant under this transformation. And the proof, so first I'm going to let CZ be my cross ratio Z, Z2, Z3, Z4, and R of Z to be Z, TZ2, TZ3, TZ4. And then what you have is here is a circle that goes through Z2, Z3, Z4. So I don't know, somewhere here is Z2, somewhere here is Z3, somewhere here is Z4. I chose, let's say I chose orientation that is counterclockwise. Doesn't have to be, by the way, right? It could be clockwise. So let's see what happens, right? So what is CZ gonna do? CZ is just gonna take this and map it onto the real axis. So this is the point Z2 carried here, this is the point Z3 carried here, and Z4 is carried to infinity. Okay. Now, what is going to happen if I apply T to that circle? If I apply T to that circle, it's going to be another circle. Do you agree? It's going to be another circle, and the points. I'm not sure if they would preserve this orientation, but let's say this is T of Z2. Somewhere here is T of Z3, and this is T of Z4. Okay? Now I apply R. I apply R. What's going to happen if I apply R to it? So this is T applied, now I apply R. What's going to happen?
Given orientation.
If I apply R, it's back to the same line. Back to the same line. When we'll finish a proof, I'll give you a rigorous proof of it, but I want you to see why you would notice that this is invariant. It's back to the same line. Look at it, right? A map, when you look through a map, right? This transformation, TZ, TZ2, etc. This is just R composed T. This is T, and then we go through R. Okay, R composed T. Now, what is R composed T? Forget about the middle ground. What's really going to happen? R is going to map TZ2 to Z2 to 0. Sorry, right? TZ3 to 1 and TZ4 to infinity, right? But if you have R composed with T, what is R composed T going to do? It's going to map Z2 to 0, Z3 to 1, and Z4 to infinity. So if you just ignore the middle ground, you obviously see that you're getting the same exact picture, right? So let me just give you a rigorous proof. You think about it. It's, by the way, nothing is special about cross ratio. This will be true with any other Mobius map. You can create a suitable invariance for other maps. And just the reason cross ratio is interesting is because, again, when you begin thinking about this, it's easier to deal with this with the real line, right? The real axis is the easiest type of circle you can think of, I suppose, right? Its geometry is very simple, so that's why you like cross ratio more than other Mobius transformations. That's why you begin with it. Okay? With it. So here is the rigorous proof. And then I'll let you go with it. Right? When do we finish? At 6:55 or at 6:50?
6:50.
All right, so we'll finish this proof and then you can go. So, yeah, so what we do is we look at R composed with T and composed with C inverse. And I want to show what about this map? I want to show it is what?
So the composition is equal to,
What was your C?
Well, my C is my ordinary cross ratio in Z2, Z3, Z4. What do I want to show about this? Yeah, absolutely, because then I can just move the C across, right? It's identity, and I can move the C across, and I prove that there is invariance under this transformation. And that's very simple. We want to show this is identity. Which is obvious, again, from the picture if you think about it.
The identity on the line, right?
No, identity everywhere on the complex plane is the identity. So how do I do that? Well, there are only several values that you can try. RT, compose C inverse, what are you going to plug in? 0, right? Of course, right? 0, and what's going to happen? So that's going to be R, compose T of Z2, right? And that's going to be R maps TZ2 to 0, right? And then, so that's 1, 2, R compose T inverse of 1 is R composed T composed of T of Z3, right? And that's R is mapping T of Z3 to 1. So again, you see 1 is fixed, and once we know 1 lastly, and then a member is fixed, that's it. You have it done. So 3 R composed T composed C inverse of infinity. That's going to be R composed T of Z4, which R maps T of Z4 to infinity, right? So we have 3 fixed points, so everything is done. 3 fixed points, right? And done. It's the identity. Okay, but again, you can see that by this picture. You see that this is just giving you an intermediate step. So functions are just like black boxes. So you care about what you began with and what you end with. And since you end when you begin with the same thing, you end up with the same thing. The two maps must be the same. Okay. So I guess I'm going to release you. I'm sorry. I wanted to cover much more. I wanted to completely finish Mobius transformation. There's a few more things that I want to say, because this is going to imply that we can map one circle to another circle, and then I want to talk about what happens to interiors of circles, right? So if I look at the interior of the circle, what's Mobius transformation going to do to it? At least a little bit, right? And one last warning is that if you look into Conway defines the cross ratio to be going in the negative direction. So it says it's going to map Z2 to 1, Z3 to 0, and Z4 to infinity. So you see you move 1, 0 to infinity, so you're moving in the opposite direction. And therefore my formulas are slightly different than Conway's formula. Okay? I don't know, I mean, I know, I think really why. It's because he wanted the unbounded region to be mapped to the unbounded region. That's really why he chose this orientation.